let's go back to our agenda. So let's dive into stepper motor. So what is stepper motor? Stepper motor is a brushless DC motor that divides its full rotation to the equal number of steps, and its step angle defines the resolution of the stepper motor. The stepper motor can operate on a open loop since the angle of the rotor is defined by the number of steps. It is normally can be seen in printers and conveyors, and as mentioned, the angle of the stepper motor is equal to the step angle multiplied by the number of steps. Okay. So there are different types of stepper motor. We have variable reluctance, permanent magnet, and a hybrid type. The variable reluctance uses a non-magnetized rotor. It the rotor rotates to a position that gives minimal reluctance. So let's go to the variable reluctance stepper motor. So the variable reluctance stepper motor operates on a variable magnetic flux due to varying reluctance. The rotor of variable reluctance stepper motor is a ferromagnetic non-magnetized core. In other words, it is non-magnetic, but it can be energized to be a magnet because it is a ferromagnetic material. Similar to an electric circuit, magnetic circuit also has a source, which is refers to as the magnetomotive force. If magnetomotive force is the source, the electric current is the magnetic circuit is referred to as the magnetic flux. And with that, the resistance is referred to as the reluctance, which is the quantity that opposes the flow of magnetic flux. The magnetic reluctance of the material can be determined by dividing the magnetic motive force acting on a material by the total magnetic flux of that flows to it. But since it is impractical to measure the flux or the magnetic flux to get the reluctance, the equation was further simplified. So the magnetomotive force is equal to the current multiplied by the number of turns, and the magnetic flux is equal to the dot product of P times A. Since magnetic flux is equal to since the magnetic field is equal to the permeability of the material multiplied by the magnetizing force, it can be further simplified to this. As you can see here, the magnetizing force is equal to the current multiplied by the number of turns divided by the length of the rotor. Since the current multiplied by the number of turns can be cancelled out, that means the reluctance of the rotor is equal to the length of the rotor divided by the permeability of free space divided by the permeability of the material or the relative permeability of the material and the area of the rotor. The area of the rotor here shown in the equation is the surface area of the rotor which is in contact magnetically with the magnetic poles. Here, this is the area So, how does the reluctance varies if the length and the area is fixed? Since the magnetic flux is B dot A, that means it is equal to the magnitude of B times the magnitude of A multiplied by the cosine theta. In this reluctance equation, since this is a rotating magnetic field, there is this reluctance would be multiplied by the cosine of theta. In other words, if the area and the magnetic field is completely perpendicular, that means the reluctance is maximum and the flux would be minimum. And if the area and the magnetic field is in parallel, the reluctance is minimum and the magnetic flux is maximum. If we create a diagram of this magnetic field, it would be like this. We have the source or the magnetic motive force, the reluctances of each magnetic components here. It is assumed that the reluctance of the core would be very, very large compared to the other components, so we can neglect it to make the circuit simpler. So we're down in two components, the air gap, the reluctance of the air gaps, and the reluctance of the rotor. As mentioned earlier, if the rotor is completely perpendicular to the magnetic field, similar to our case here, the reluctance is minimum, the reluctance is maximum. Therefore, the flux is smaller. This small magnetic flux enters the top part of our rotor and leaves the bottom part of the rotor. By using the principle that we have learned earlier, that the flux leaves the north and leaves the south, that means this ferromagnetic core, this ferromagnetic non-magnetized core, would be magnetized by the core's magnetic flux, similar to this. And as the motor rotates, the magnetic reluctance decreases, which creates a higher magnetic flux. This is why the variable reluctance, it is mentioned earlier that the variable reluctance rotates to a position which gives minimal reluctance. So as you can see, the step angle or the step size is equal to the 360 degrees divided by 2 multiplied by the number of pole pairs. Next is our permanent magnet stepper motor. The permanent magnet stepper motor, of course, is made from a permanent magnet rotor. The step size increases with the number of rotor poles. And as you can see here, there will be a force of attraction and repulsion that is experienced by the permanent magnet rotor due to the the poles. So this north magnet would be attracted by this south magnet, and this north magnet will also be attracted with this south magnet, similar to this. And again, after that commutation, we are about to change the rotor or the pole's position, similar to this. And again, this north magnet will be attracted by this south magnet, and this north magnet will also be attracted by this south magnet, and it will continue until the last revolution or the until it uh, became a one revolution. And the step size of the permanent magnet stepper motor is equal to 360 divided by 2 multiplied by the pole pair. The hybrid stepper motor. This is how hybrid stepper motor looks like. Basically, the major difference is that this hybrid stepper motor has a south and north cap wherein it is positioned alternately. So it's the same as the others. It has stators and windings. This is has but this hybrid stepper motor has this south cap and north cap, which is a permanent magnet. To clearly see a hybrid stepper motor works, we should check the cross section. First, we can see that it comprises of 50 north teats. It also has 50 south teats, and the north or south are positioned the north and south are positioned alternately, similar to what's shown. It is also has a 48 poles positioned in such a way that the vertical poles are positioned are completely unaligned with the south magnet, similar to this. So as you can see here, the vertical side is completely aligned with the south poles, and the horizontal side is completely unaligned with the south rotor. Take note that if it is completely unaligned with the south rotor, it is perfectly aligned with the others. So this pole is positioned in such a way that it is half aligned, as you can see here. These poles are half aligned where the pole are ahead of the south rotor, as shown here, while this rotor is is half aligned, rather, wherein the pole is behind the south magnet, as shown here. So let's check how this hybrid stepper motor works. So in this position, this south magnet is attracting this north magnet here. Similar situation here, here, and here. When we reverse the pole position, it will become here. And then, as you can see here, this north magnet will be attracted by this south magnet until it is completely aligned to each other. Similar case with here, here, and here. So after after that, as you can see here, the step size of the stepper motor, the hybrid stepper motor, will be equal to 360 degrees divided by 2 divided by n, the number of north teeth plus the number of south teeth. In this situation, since it is very difficult to draw a 50 teeth and a 50 teeth north and 50 teeth south, I just use 18 teeth. So I have 18 teeth on the north side and has 18 teeth on the south side. And if that, with that, I will be having a 5 degrees step size, similar, like this. So these are the stepper motor types according to its cost and performance. The earlier version of the stepper motor is the reluctance type or the variable reluctance type stepper motor. It is um, its cost is very low because it's non-magnetized. As you increase the performance, the cost would also be increased. And the hybrid stepper motor has the best performance because it has a lower step size, but it is the most expensive among the three types. Do you have any questions before I can continue? So let's go to the difference between the bipolar stepper motor and the unipolar. So let's check how the bipolar stepper motor is construction is. First, we have M1 and M1 bar coil, which is connected to each other. Again, we also have another M1 and M1 bar, and these two coils is connected to each other to make one phase. Next is we also have M2 and M2 bar and another M2 and M2 bar. And these two coils are again connected to each other, and this makes phase 2. What if I connected a positive terminal or a positive voltage here at the top and the negative voltage below, similar to as shown? It is expected that the current will be flowing downwards and similar to what's shown in the diagram. And with that, the corresponding coil will be energized as shown. And what would happen is that this north magnet would be attracted with this south magnet. And similarly, this north magnet will be attracted by this south magnet. So what would happen is that it will be attracted until it is fully perpendicular to each other. So after it is being attracted fully, we can change, we can now activate or we can now energize phase 2 by placing a positive terminal at the top and placing a negative terminal below. With that, it is expected that the current will be flowing downwards and accordingly. And with that, the corresponding poles will be energized as shown. And if poles are energized as shown, this north magnet will now be attracted with this south magnet, and this north magnet will now be attracted by this south magnet. Okay. For the next iteration, I will be placing a positive terminal below and the negative terminal above of the phase 1 or the first phase. And what would happen is that, and again, I will reverse the direction for phase 2, and I will be doing that until the entire revolution is complete. Okay, how about the unipolar? How does it looks like? Similar to a bipolar stepper motor, it also has M1 and M1 bar. It also has another M1 and M1 bar, and it also connected to each other. Again, it also has M2 and M2 bar, which is connected to each other. The difference is that at the middle of this terminal, we have connected it to common, and this common is normally connected to a positive voltage. So how does a unipolar stepper motor works? If this is positive and I connected a negative voltage here, it is expected that the current will be flowing in this direction. And if the current flowing in this direction, the coil will be energized as shown. Take note that the top part of the phase of phase 1 is not energized, only the bottom part. And with that, the force of attraction and repulsion will only be occurring on the bottom part. In this case, this north magnet will be attracted by this south magnet. There is no force of attraction by this north magnet to this pole because this pole is not energized. So let's see how the rotor rotates. Okay. After that, if I change the coil such that I place a negative terminal here, the current will be flowing in this direction. And the coil or the poles will be energized accordingly. Notice that similar to phase 1, phase 2, only the bottom part is energized. The top part is not energized. And with that, only this north magnet will be attracted by this south magnet. There is no force of attraction by this north magnet to this magnet since M2 is not energized. So let's see what happened. Okay? Then, what if I place a negative terminal at the top of the phase 1, such as shown? It is expected that the current will be flowing upward and it will energize the coils accordingly. So since the bottom part is not energized, it is expected that there's only be a force of attraction from this north magnet to this south magnet. There will no be force of attraction from this north magnet to this magnet since this is not energized. So let's see how this will rotates. And if I place a negative terminal on this phase 2, on the top of the phase 2, it is expected that the current will be flowing upward and will generate or energize the coils accordingly. And with that, since only the top part is energized, there will be no force of attraction at the bottom part, only here. And doing the same thing all over again will make the stepper motor rotates until it reaches 1 revolution. So, based from what we have seen, since there is only one force of attraction and repulsion per iteration in the unipolar stepper motor, it is expected that the torque in the unipolar is less than the torque of the bipolar. Let's check the stepper motor that we will be using on our experiment. So we are using a hybrid stepper motor. So these are a mechanical specification. You will see the step angle. We have 1.8 degrees per step. We have step angle accuracy, some temperature parameters, the insulation resistance, the electric strength, the axial and the radial play. So we are using the 42HS03 model. As you can see here in the connection column, it can be connected in bipolar and unipolar. If in bipolar, it can be connected in parallel or in series. The motor length, this is a physical characteristic. This the same for everyone, but you can see the holding torque. If it is a unipolar, it is lower than the bipolar. And if it is a um, it it never depends whether it is series or parallel. It has the same holding torque. It has 8 leads. Um, the phase current, since it is in parallel, it would be 1.4. It is higher than the series one. The phase resistance, the phase inductance, the rotor inertia. This is what we have in the introduction to motor part, and we have a detent torque and the weight of the motor. What we notice in this stepper motor specification is that there is no input voltage. Why is that? Because it is not that important on what voltage that the motor operates. As long as it is below the maximum allowable voltage, we can control the stepper motor. Is there any question before I can continue?